We're going to talk about arc length next. Arc length is the distance that we've traveled around the circle. This is closely related to our definition of the radian. So to travel 1 radian, I know that I get to 1 radian when I've traveled the same distance as my radius. So r is equal to r. And this distance right here, theta, is equal to 1 radian. This is really helpful when we're talking about the arc length because we're able to associate the radius of the circle with the arc length traveled as long as our angle measures are in radians. One really nice example of the arc length is the circumference. So the circumference is the distance around the entire circle. So circumference is equal to, or you can think of that as the arc length when my angle is equal to 2 pi. So if I take a look at circumference, it is the distance all the way around the circle, one full rotation. So I know that circumference is equal to 2 pi r, but I've also traveled 2 pi. So in general then, I can write this as theta times r. So in terms of my arc length, so arc length, we denote that with s, circumference is a special case, is equal to theta times r, and theta has to be in radians. We're not going to be doing any examples with velocity, but I do want to put it up here because it's a really helpful tool and something that this material is foundational for in terms of physics and definitely calculus. Velocity, you can think of that as speed, like when you're driving your car, you're going maybe 30 miles per hour. Miles would be your distance, and hours would be your time. So it's distance over time. We can think of velocity in several different applications in terms of rotations. So when we're looking at these in terms of rotations, we could talk about what arc length has been traveled over time. And we're thinking of this as maybe some kind of a satellite out in space. I don't know how to draw a satellite like that, maybe. I don't know. So it's a satellite that's traveling out in space like that. That's better. So we can talk about the distance it's traveled along its path, but we can also talk about its rotation. So theta over t. This is our angular velocity. But we're going to be focusing today on the arc length. Let's go ahead and look at some examples. Remember, the key is that that arc length is in radians. So we want to start by finding the arc length subtended or drawn out by an angle of 90 degrees for a circle of radius 3. So my circle is radius 3, 1, 2, 3, and I'm going to go ahead and draw out an arc length using 90 degrees. Well, first of all, S is theta times r, but theta needs to be in radians. So 90 degrees is equal to pi halves radians. So I'm going to write this as pi halves times 3. So this is going to equal to 3 pi halves. And this is whatever units the radius is in. This is not radians. I can use my calculator to get an approximation here. Okay, I already have it up there, but I want to clear it and start again. So I'm going to go 3 times pi, which is right on that caret key. So second pi divided by 2. And this will give me a decimal form, so about 4.7 units, whatever our units happen to be, inches or whatever. So about 4.7 units. And I can write squiggly, so it's about. So about 4.7 units. Okay, next, number 2. I've got a circle of radius 5 miles, and I want to find the length of the arc that subtends a central angle of 6 radians. So 6 radians. If I were to travel a full rotation, that would be 2 pi radians, or 2 times about 3.14. It's a little more than 6. So for this one, I'm looking at going almost a distance of 2 pi. So I've got 6 as my radians, so theta is equal to 6, and r is equal to 5. So really, as I put this one together, it's pretty darn easy. S is equal to theta in radians, which is 6, r is 5. I'm going to pick up the units of my radius, which is miles. 6 times 5 is 30 miles. Okay, 30 miles. Number 3, this time we want to find the angle. So we're given a circle of radius 6 feet, so r is equal to 6. an arc length of 4 feet. So this is my S. S is equal to 4 feet. And I want to find the angle that we've traveled through. So if I think about this, I've got 6, 1, 2, 3, 4, 5, 6. I haven't gone a full radian. Instead, I've gone maybe that far. That's going to be 4. And I want to find this angle theta. So if I were to go a full radian, my arc length would equal 6. Putting this together in our formula, S is equal to theta times R. We do have S, which is 4. Theta we do not have, and we've got 6 there. These are both in feet. I'm just going to use the feet symbol there. If I divide everything by 6, I'm solving for my angle measure. Feet's going to cancel, and I can also reduce 4/6 into 2/3. So 2/3 is equal to theta. But remember in our formula, theta is in radians. So this is in radians as well. But I want my answer in degrees. So I've got to do one more adjustment. I'm going to take that 2/3 and I'm going to multiply it so that I end up with, this is radians, so I end up with degrees instead. So I'm going to go 180 divided by pi. Let's go ahead and simplify. 3 into 180 is 60. So theta is equal to 2. Radians would cancel because that would be radians in the denominator. 2 times 60 degrees or 120 degrees. And I forgot my pi, didn't I? All divided by pi, all divided by pi. So in my calculator, I can get an approximation. That would be my exact answer. So 120 divided by pi, divided by 3.14 whatever. So 120 divided by pi. So my degree measure is about 38.2 degrees. So theta is about 38.2 degrees. And that really matches our picture. So it's pretty close there to 38.2 degrees.